Okay, we're going to be doing lead code 235, lowest common ancestor of a binary search tree. So you're given a binary search tree and you're supposed to find the lowest common ancestor node of two given nodes in the BST, right? So according to the definition, so you're given two nodes, not two values. So the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants. So as you can see here, ancestors can only be this node, this node, this node, this node. This can't be an ancestor because it doesn't have any roots, right? It doesn't have any values. This can't be. So basically all the leaf nodes can't be ancestors, right? But the way we solve this is we check whether P and Q, right, these two nodes, are in the same subtree, right, if they're on the left subtree. Or we check if they're on the right subtree. If they are not on the left subtree and they're not both, we check if they're both in the left subtree or if they're both in the right subtree. And if they're not in either of these, then it means we found the point at which they split up, where one is in the left and one is in the right. So since we've reached that point, we just return where our current pointer is. So we have a current pointer that traverses through this BST. And then we check whether the value at our current node, if it's larger than both of them, then it means they're both in the left. If it's larger than, if it's smaller than both of them, then it means they're both in the right subtree. Otherwise, it means one of them is in the left, one of them is in the right, and we simply return current. So let's code it up, right? So we have I'm also going to draw it, so don't worry. We have a current pointer to the root. So car is equal to root. And then while car, which is the same as car does not equal to none, we check if both are on the left side, right? So if p.val is less than current.val and q.val is less than current.val. That means they are both alternative alt is current.val is greater than p.val and current.val is greater than q.val. Means both P and Q nodes are in left subtree, right? So we move our current to the left subtree. Current is equal to current dot left. Remember, we don't know exactly where they are, we just know they're both in the left subtree. Elif p.val is greater than car.val and q.val is greater than car.val, then the alternative to this is car.val is less than p.val and car.val is less than q.val. This means both nodes are in the left, in the right subtree. So we move our current to right subtree. So current is equal to current.right. Else, we have found else. What else means? One of the nodes is in the left subtree and the other is in the right subtree. So we are at the point at which they both split. We are at the point at which their LCA is on top, right? Or where they split, right? Because these two nodes will never be on this in the same node, right? They'll be either on the left and the right, right? So it's just about finding who their ancestor is, right? So either they'll be directly below the current node, or they'll be somewhere buried here and somewhere buried here. So we simply return current as LCA, and then we return car. So our pointer car will always end up at this position for any two nodes, right? So you don't need to, wherever our current will always end up at the point where they split up, right? Because anytime we realize they're both in the left subtree, we just go to the top of the left subtree, right? Because we know they're both somewhere inside here and they can't be at one position, right? If we know they're both in the right subtree, we go this side. And we know they can't both be here, right? It means they are somewhere here. So let's run this and see. Voila, it works. So what we're going to do is we're going to do some drawing so that you understand this properly, right? We're going to put this code to the left, and luckily Professor Roger already got it here. So what we're going to do is we're going to iterate through following the code. So our current pointer is now here, right? Our P and Q, which we're looking for, are these nodes, right? So we ask ourselves, so we're at this code, right? Is our current none? No. Is P.val less than current val? And Q.val, are they both less than 6? No, they are not both less than 6, right? They are not both less than 6. Are they both greater than 6? No, they are not both greater than 6. So that means we have found the node where they both lie below directly, and this is our current node. See that? Our current node is the node at 6, which is what we return. All right. So let's go to another one. You see where our 7, we want to find the lowest common ancestor of 7 and 9, right? Here we can obviously tell it's 8, right? But we're going to use our code. So when we look into our code, we initialize our current pointer to the root. Let me write it like this. So we initialize our current pointer to the root. Is current none? No, it's not. We come down to this code. Is P.val less than current and Q.val less than current? No. Is P.val greater than current and Q.val greater than current? This code right here. Yes, they are both greater than the current. So we push our current to the right side. So it comes here, right? So we obviously don't come to this, right? Because we've gone for this condition. So we come back to this code. Is current equal to none? No, it's not. is p.val less than current and q.val less than, okay, is 7 less than 9? No. Is 8, is 7 less than 8? Yes, it is. Is 9 less than 8? No, it's not. Okay. So is 7 greater than 8? No, it's not. Is 9 greater than 8? Yes, it is. So we are skipping these two conditions, right? It means one of them is on the left and one of them is on the right. So we simply return our current, which is 8, right? So for, okay, then let's go to the next one, 3 and 8. We initialize our current pointing here, right? So we ask ourselves, is 3 less than current, which is 6? Yes, it is. Is Q less than our current? No, it's not. So obviously we know that both are not greater than, right? Because 3 and 8. So we simply return 6 as the lowest common ancestor for 3 and 8, right? So this is our answer, right? We simply return this current. So then to the last one, 3 and 9. We initialize our current to this, right? In the code, right? We initialize our current to the root. Obviously, both are not less than the current value because 9 is equal to, and both are not greater than the current value and both are not less than, so we simply return the current, which is 6. This is for 3 and 9. Their lowest common ancestor is the 6. So that is the code, right? We can check our answers to see, right? We can run this and see. So let's do console, right? Test case. We started out with 2 and 8 and we got 6, right? So let's run that and see, right? You see? Our test case was 2 and 8, which is the same we have in our diagram, and our answer was 6. So what was the next one we did? We did 7 and 9. 7 and 9, and we got 8. Let's run it and see. You see 8. Then we did 3 and 8. 3 and 8. Let's run it and see. What answer is it going to give us? 6, which is what we got in our diagram, as you can see. Then finally, we had 3 and 9. 3 and 9. And we get 6, which is what we got. So this is an O of n solution if we have a skewed binary search tree. And constant space, because we're not like saving anything in our value and we're not using recursion, right? So we're just using a pointer to go through. And the thing is that if it was a balanced binary search tree, then this would have been log n, right? So yes, that is the solution to LeetCode 235, lowest common ancestor of a binary search tree. Thank you and bye. Oh, it gave me 55. Let's try to get 90. Come on, give me 90. 41, give me 90. Give me 90. Okay, I got 80. That's fine. All right, so thank you and bye.